Alright, good people. Welcome to Algebra 2. I'm very excited to be here. I hope you are too. Before I get started on our first video, which I'm very excited about, what I'd like to do is just explain what's going on down here. At the bottom of each page, you're going to notice that there's a place for questions. I really want you to, as you're going along, if you stumble upon something that I haven't explained very well, or just is very foreign to you, or something that comes up in your mind that is not answered, and you either don't feel like Googling it or texting a friend or emailing me or whatever, here's a space for questions, and I want you to use this. In fact, I'm requiring you to use it so that every day you at least bring some questions in to class after watching the video. No video is perfect in explaining everything, and it's not interactive. You know, you're just sitting there watching, and then a question might come up. So I want you to write down in this space. You might say it's like number 10, for example. Number 10, I just don't get. Or what's a real number? Or whatever it is, just make sure you write down some questions to bring to class, because no video is going to cover everything, and no user experience is going to be great. Perfect enough to answer all your questions. You've got to have some questions. So in that space, write it in. Next is an audio check. In my previous school where I did this, I noticed that there's a disturbing trend, and that students were starting to listen to videos. They were watching the videos without listening to them. So one thing I'm going to try to do with every single video is I'm going to have an audio check, and it's information that's only going to be displayed purely with audio. Like, you won't be able to see it. And it'll be personal information about me, or just random information I'll throw out in the middle of the video. And when you get to that, then I just want you to write down the audio check, and I'll show you what that means real soon, because we're going to do it right here. The number system. All right. So I love explaining the number system, because although this chart here, this picture might look a little gnarly, what I'd like to do is just talk about the number system in terms of cities in North America. So check this out. Cities in North America. So numbers are a lot like cities in the way that they're organized. So you can have a whole group of cities in the United States of America. There's New York City, there's Los Angeles, there's Seattle, Chicago, and there's also Philadelphia, Harrisburg. All these cities right here, you're going to notice, are all in the United States. And there are other cities that are not in the United States, but still in North America. So the ones in Canada, like Montreal, Quebec, the Mexico City, Guatemala City, which is actually an awesome place to be. Check this out. Guatemala City I spent 3 years in Guatemala City. Personally, that's where I lived. Me and my wife. I taught there, and she was a worker there, so it was really awesome. So check this out. When you get to personal or random information that doesn't necessarily apply out of the textbook, that's your audio check. And I'll even say audio check that. So you can say Guatemala. Bergman lived in Guatemala City for 3 years. I'm giving you the first audio check. Normally it won't look like this. You'll be the one writing it in, just to make sure that you're actually listening. Alright, enough of the distractions. Let's go back to the real stuff. So, cities in North America. Now, there are lots of cities in the United States, and some of them are cities in Pennsylvania. So here are some cities that are not in Pennsylvania, and here are some cities that are in Pennsylvania. So these: Philadelphia, Harrisburg, State College, Pittsburgh, they're all in Pennsylvania, as are these: Abington Township, Cheltenham Township, Norristown. But you can go one step further. There's the cities in Montgomery County, and for those of you who are not from Pennsylvania or not from the area, then Montgomery County is a county inside of Pennsylvania. And I think all of these, I could be wrong, maybe a local who's been here longer than I have can correct me, but I do believe that all of these are cities in Montgomery County. Now, these are also cities in Pennsylvania, and these are also cities in the United States, and these are also cities in North America. they belong to a small group, but they also belong to each other large group. So, if it's true about a city, if something is true about one of these cities, if Abington Township is in Montgomery County, then it's also in North America. Just like Quebec is also in North America. Alright, so let's apply that logic to the real numbers. Check this out. Now, every number that you know of so far, pretty much, and most of the numbers that we're going to be talking about in the entire class are called real numbers. There are some numbers that are not real numbers, and those just blow my mind, and I hope they blow yours too once we get to it. But for right now, we're going to talk about all the numbers in all the numbers that we talk about are going to be real numbers. And what are the real numbers? They're just all the numbers on a number line. So if you can put the number on the number line, then we'll call it a real number. That's pretty much every number you know. You know, there's the square root of 3 and negative 8.3 and negative 1 and the number 5. Those are all real numbers. Now there's a special category of real numbers called rational numbers. And those rational numbers are numbers that can be made into a fraction. If it can be made into a fraction, then it's called rational. And the word rational even comes from the word ratio, which is another kind of a word for fraction. So decimals, if you look at the decimal version, the decimals either terminate or they repeat. So, check this out. Here are some numbers that can be made into fractions. This negative 8.3, that can be made into a fraction. It would just be negative 83 over 10. Boom, made into a fraction. 5/6, it is a fraction. 17/3, it is a fraction. Even this one right here can be made into a fraction. This would be just 18 over 99. Don't believe me? Ask a calculator. Take 18 divided by 99, you get that awesome repeating decimal. If a decimal repeats in a block of repeating digits over and over and over again the same way, then yes, it is going to be able to be made into a fraction, and there it is. Even numbers like this, like the number 3, can be made into a fraction like this, 3 over 1. Done. That counts. 0 could be really 0 over 1. It's a fraction. It can be made into a fraction, therefore it's rational. Here are some numbers that can't be made into fractions. So numbers that can't be made into fractions are the square root of 3. It's just this really long decimal that never completely repeats. In fact, there it is, 1.732050807569. This decimal does not repeat at all. By the way, if I write something down, I want you to write it down. That's the rule here. If you're wondering, like, how should I be doing this? Well, you should be doing this with the notes in front of you, printed out, and a pen or pencil in hand, and I want you to write down everything that I write down. If you see me write it, then I want you to write it too. Okay, so there it is. These numbers cannot be made into fractions. Pi, people have tried. They've gotten close as they want to being made a fraction, but the actual true value of pi cannot be made into a fraction. And check this out. Here's another decimal: 1 0, 2 zeros, 3 zeros, 4 zeros, 2, 3, 4, 4 zeros. Although there is a pattern, it doesn't. And the pattern, you could spell out this decimal as for as long as you want. It technically is not a repeating block of digits, so it's not repeating, therefore it cannot be made into a fraction. Alright, so let's keep on going. Those are rational versus not rational. Integers are the numbers that have no decimal, so they're both positive and negative. If they are positive integers, then you call them the whole numbers. And then there's also natural numbers. Notice that the only number that is a whole number and not a natural number is right here. 0. 0 is a whole number, but it's not a natural number. All the natural numbers are definitely also whole numbers. And the natural numbers are also integers. And they're also rational numbers, and they're also real numbers. So, let's check this out. 1, yes, it is a rational number, just like I said. It's a natural number, therefore it's also a whole, therefore it's also an integer, and a rational, and a real. Yes. 3/4 is not a natural, not a whole number, not even an integer, but it can be made into a fraction. It is a fraction, so therefore it's rational, and it's also real. -6 is not a natural number, it's not a whole number, but it is an integer, and therefore it is also rational and real. 0, whole, integer, rational, real. It's not a natural number. 19, yes, all of these. It's a natural number, therefore it's also all the others. -8/7, well, it can be made into a ratio, into a fraction, but it's not any of these, and therefore it's also real. √7, it's not even rational, can't be made into a fraction, but it is a real number. Okay. And the first 6 problems, I think, look like this. You have to figure out, are they natural, whole, integer, rational, or real? And I would recommend that when you go to do your homework, you just set them up like this, and you'll see, there it is. You make a quick little table like that, and then you'll be able to keep track of everything, and it'll be a lot more organized. Alright, so let's figure out, are these rational or irrational? Can they be made into a fraction? Well, this one, yes, it definitely can be. And this one, if you simplify it, it can be made into a fraction. It's -8/1, so yes, it is rational. 7.42 is just going to be 742/100. That can be made into a fraction. Besides, the decimal terminates. Here, it doesn't. The decimal terminates. The decimal does not. Number 8. The decimal does not terminate, but it does repeat. Therefore, you could say it's 47/99. That is the fraction. Therefore, it is rational. But here, in number 9, there is no pattern whatsoever, and the decimal does not stop. Therefore, we're going to say it is irrational. I'm going to cross out the irrationals, and I'm going to circle the rationals. √27, you look at the decimal, and there's just no end and no pattern, so therefore it is irrational. One thing I wanted to mention is set builder notation. A set is just any collection of things, usually numbers. And they have those squiggly, I have terrible handwriting. So like 0, 1, 2, 3. That is the set of all whole numbers. It's a collection of numbers, and this is how you build it. Well, and I think this is called roster notation. You've got a roster of all of them. You've listed them all. Great. There's another way to do it, and it's called set builder notation. And what it would look like this is, you read this as all x, every value x, every number x, such that, the line means such that x is divisible by 2. So if a number is divisible by 2, then we want it to be in this set. And this set is a collection of all the numbers that are divisible by 2. So here they are, I've listed them out, they're all the even numbers. So these are two different ways of describing the same collection of numbers. One is a way that uses a rule, and that's over here. This is the rule. And then the other is a way that just lists them all out as a pattern. Set builder notation gives you the rule to build the sets. So the really cool thing that I love about these laws here is that they are what you need in order to create a lot of different ideas. These are like the foundational building blocks of algebra, really. And so just to be very clear of what we can and we can't do, we typically at the very beginning of the year enjoy talking about the operations, addition, subtraction, multiplication, division. And are they commutative? Are they associative? What's the identity? What do we mean by inverses? And then also the distributive property. So check this out. So in addition, the really cool thing about addition is that you can switch up the order. 3 plus 4 is the same thing as 4 plus 3. That means addition is commutative. The order of the numbers doesn't matter. That's not very true of subtraction, because 3 minus 4 is not equal to 4 minus 3. So subtraction is not commutative. I'm going to cross that out on your paper. Very important. Is it true of multiplication? Yeah, 3 times 4 is the same thing as 4 times 3. I'm going to confirm that. Yes, it's true. Yes, it's true. Because in the others, division, 4 divided by 2, that's not the same thing as 2 divided by 4. So division is not commutative. Subtraction is not commutative, but addition and multiplication are. Associative, the order of operations doesn't matter. If you've got several additions in a row, does it really matter which one you do first? No, addition doesn't matter. Because 4 plus 3 is 7, plus 2 is 9. And then here, on the other side, you've got 3 plus 2 is 5, plus 4 is still 9. So it doesn't matter what order you do operations. Addition is associative. Is that true of subtraction? Nope, not true. Because you do those two separate sides of the equation and they are not equal to each other. Multiplication, yeah. If you have a whole lot of multiplication, I'm just going to keep this right here. If you have a whole lot of multiplication, then it doesn't matter which multiplication you do first. It's still going to give you the same product. In this case, it's 24 on both sides. But division, no. Because 36 divided by 6 is 6, divided by 2 is 3. However, if you do the other side, you get an answer of 12, and 3 is not equal to 12. Identity, looking down here on the next row, identity for addition, well, what is the identity? The identity is the number that produces no changes. So, for example, when you're talking about addition, 0 is the identity, because 5 plus 0 is still just 5. There's no change. Subtraction, if you wanted to, you could call 0 also the identity. So addition and subtraction are very much related in this way. Multiplication, 1 produces no change. Division, 1 produces no change. Why is that a big hairy deal? Well, I'll tell you why. Because the inverse is of their inverses are pairs of numbers that produce the identity. So what produces the identity in addition? Two numbers, 8 and negative 8. If they produce the identity, then we call them opposites or additive inverses. Let's not talk about subtraction or division, but I will say that two numbers that produce the identity in multiplication are, for example, 8 and 1 over 8. So 8 and 1 over 8 are multiplicative inverses. And we call them, in this case, we call them reciprocals. Opposites and reciprocals. The distributive property here, distributive property just tells us the relationship between multiplication and addition. And many of you have seen this before. I do want to make sure that you know that when you multiply by both numbers to get 15. Here's the common mistake, that you forget to multiply both. 3 times 1 and 3 times 9. 3 times 1, 3 times 9. And in general, it looks like this. Now, what I'm going to do for the rest of these is I'm just going to say these are problems that you should be able to as an Algebra 2 student. You should be able to do these things. And I'm just going to not make the video any longer and just turn you loose. I want you to do these problems. And then, when you finish these problems, I want you to start your homework. So when you finish watching the video, when you finish doing these problems, I want you to start your homework and at least do the first problem. At the very least. That way you'll know whether or not you're going to have an easy transition into doing the assignments. And actually, I don't call anything homework in my class. I'm going to call them the assignments. Start your assignment 1A. At least do the first problem in assignment 1A. Make sure you write down all the problem numbers in your composition book, and we'll talk about them in class when we get there. Take care, and I'm looking forward to a great year.